In this video, we'll take a look at using Ansys to perform an analysis on a beam and shell structure. We'll start by importing a CAD file into SpaceClaim, preparing the geometry for analysis, and then heading into Ansys Mechanical to actually analyze the part. Our first step is to insert the file. So let's go out to my disk here and find it. It's a .sab file, so we'll bring it in. SpaceClaim will open it up and we'll see that it's a nice file coming in. Not quite ready for actual analysis, especially with beams and shells, so we're going to have to do a little cleanup. First thing I notice is some problems that we need to get rid of, some stamped in pieces and a lot of extra holes that would be a real nuisance for meshing. So let's do this. We'll go ahead and hide these bodies here, and then we'll right off the bat see the power of SpaceClaim really nicely. I'm going to zoom in and just grab one of these holes here and go over to Power Selector. And I can ask SpaceClaim to grab me all holes of the equal size here and then just hit delete and they go away, which is really nice. We can also do the same thing for this middle part here for the text. I'm going to use a lasso select and go in and just grab all these little embossed faces and just hit the delete key and they go away really nicely. Next, we notice that this part is not quite ready for analysis. We've got a mix of solids here and shells that are sort of brought together in a way that look like solids, but they're not actually solids. So that's going to give us trouble. We don't want our shells that we want to analyze to actually look like that. So good news, SpaceClaim is really good at handling stuff like this. We can use a stitch tool that goes in and looks for everywhere where we have that situation and is going to offer to stitch them together. It's saying it found 9 areas for that, so let's give it the OK there, and sure enough, voila, it turns all those into actual solids. Really convenient tool. However, we don't actually want to analyze solids. We want to do a mid-surfacing operation here to get these into true shells. Problem is, mid-surfacing a part like this normally be quite difficult. Different thicknesses, different ways they come together, but that is a huge strength of the SpaceClaim package. Mid-surfacing options based on something like just go in and use a range and say anything within 50 millimeters, for example. Go find what you can for me, and we can just do a quick look and see that it's found everything really nicely here. Give it an OK, and it runs forward and turns these into shells. Really good. Next, let's turn our attention to the actual beams in this structure. So the first thing I want to do is get rid of this top body here. We'll represent him separately and differently in the analysis. So we just hit delete on him. Now let's turn our attention to the top half by hiding everything down below. And taking a look at details in here, we see that these beams actually aren't that simple as structures. There's some complexity to the connections with these loops and things that make this really not that easy to turn in to beams from the current version of tubular shells that they are. The good news is SpaceClaim has a really powerful beams section, and if we simply use the beams extract tool, it's really good at figuring out what's needed and turning into beams. And it does. Now, I know we started with kind of dirty CAD geometry, so I want to run this extend tool that's going to go look for anywhere where maybe things didn't close up properly, or maybe there was some overages like this, for example. That's not good, or these gaps that were left. SpaceClaim's great at finding those and just eliminating them for you and letting you know, hey, this was a problem I think you should fix, and we do. So we're in good shape now. So next up, what I want to do is let's bring back everything, show all, and we can just click this button to get rid of the original tube structure and solid structures that we've already eliminated and just be left with our beams and shells. But by bringing these back, I want to make sure that we don't get left with this gap in here that is going to cause problems. Now you see there are some gaps. These beams don't dive down into the shells like I want them to, so we can simply run the extend tool again and look what it finds. It finds all the 12 areas where that's a problem, and with one click we can just say those are cleaned up. Really nice. Now at the same time, if you look at the cross sections, this was clearly meant such that these faces here would extend in and close up with these beams. So I want to make sure that that happens. To get that, we're going to run the extend tool, but this time we're going to do an extend to curves, and we're going to open it up a bit. Instead of 40, let's double it up and do 80. Okay, and we see that it's finding these locations right there where it's saying I think these should close in, and let's see how it does with that. And it looks like it did really nice. Really nice example of how it can just simply close all those up quickly and easily for us. So that's great. One more thing before we wrap up. I've been noticing as we fly around the model that there's these little tiny overhangs in certain areas that'll give us real trouble when we go to mesh this part. So you notice it's on this side. If I fly around and look over here, I bet you we're going to see them down in here as well, and we do. So SpaceClaim's really good at going over an entire model and finding those areas of trouble and cleaning them up. So instead of extend to curves now, let's ask it to trim surfaces and maybe get a little less aggressive than 80 and try 50. Yeah, that looks good. That's just going to grab where those overages are. We can zoom in on any area and see what it's going to work on, and then just hit OK, and it trims all those back. Makes it a really clean analysis now that I'm confident the mesher will have no trouble with and handle really nicely. One more action before heading into mechanical. I want to grab everything that we've worked on here in SpaceClaim, select all, and say throw it into its own component. Once I do that, we're left with a bunch of empty components that I can pretty easily clean up here. And we see now that all the stuff we worked on is in component 1. The original stuff is still held in this other component that we're going to remove from the analysis, and component 1 has our beams and shells. The advantage of this is that I can ask it to share topology across everything that we did. Now this is going to say that the mesh will be created such that nodes will bind this together rather than the need for contact or MPC, which is hugely advantageous in an analysis like this. Now that we're wrapped up in SpaceClaim, let's go back to the Workbench project schematic and launch mechanical. The model comes in and we can check and see that sure enough everything has been grouped into a single part, component 1, and that's going to have all our mid surfaces and all our extracted beams sitting in there ready to go. So let's start off with the mesh. Now when you're working on a beam and shell model like this, a good sizing method to use would be the uniform sizing function. So we'll turn that guy on here, and I'm going to switch my units over to millimeters and state that I want to do maybe a min of 30 and a max of 35. Try to keep everything grouped together pretty consistently, and let's ask Ansys to generate the mesh and see what it comes up with. We see what looks like a really nice mesh. Let's spin around and take a look here. Certainly the work we did to clean up those edges was well worth it. We've got a very nice high quality looking mesh. Let's get a little more of a quantitative view of it and view the statistics that come in here. Looks like very nice. The vast majority of our elements are high quality. Moving down the quality spectrum, we see that even our lowest level here is at 0.36. This is just fine. We don't have any concerns here. If I did want to take a closer look at where we might have some trouble, I could ask it to please plot element quality. That's going to show me in a graphical form where everything is. I can ask for the min and see that the worst element that we've got is over here. If I wanted to, I could do a little node moving to try to clean that up. But really, I think with the 0.36, we're in fine shape here. So we'll just move on. Next, I'm ready to turn my attention to boundary conditions. So the first thing that I want to do is work on this top structure here where we had deleted a body that was holding all these beams together up top. My goal is going to be to put a remote point in that will tie them together. Now I could go and one by one select each one of these vertices, and that's not that bad because there's only 12 of them. But what if there were 1200? I'd need a better way. So let's look at how to do that. What I'm going to do is grab this edge down here and extend it to all the ones that wrap around. And since I know that's at the center of everything, I'm going to ask for a new coordinate system. I'm going to make it a cylindrical coordinate system, and I'm going to rename it and call it the center. Okay, just some name like that. Next up, what I can do is I can request a named selection, which is really just a group of like entities in mechanical that I'm going to build off of a worksheet. This allows me to use logic to do something like add all vertices that have an X location, which is less than, I know my part, so I think this needs to be 500 millimeters, in that center coordinate system. And let's see what that gets us. Sure enough, that selects all of them that's at that location. So that looks really good, and we'll rename this, and we'll call this top verts. Something like that. Pretty nice. To use this new named selection, I'm simply going to request a remote point, and instead of basing it off of a geometry, I'm going to base it off of a named selection. We'll use top verts, and what I can do as well is I can ask it to show me a preview of the connection lines. Very simple spoke here, grabbing everything together at this remote node, at this master node that's holding things together. So I have a remote point that I can use in my boundary condition setup now, and let's actually go set up some boundary conditions. First of all, let's do a remote displacement and go grab that remote point and say that we want to bring it in the Z upwards by 10 millimeters, and we're going to hold everything else about it completely fixed. So we'll go all zeros for rotation and displacement besides that, and that's going to pull that guy up. We have to have something at the bottom corresponding to hold it together. Let's do the same down in here. Select this guy and just do a straight displacement of these geometric components downward. So in the Z, we'll pull it down -10 millimeters and hold the others fixed, just like this. We're now ready to solve the analysis, so let's do it. Everything looks ready. Let's hit the solve button. Looks like the solve went quite well. Before we dive in and take a look in the post-processor, there's a key setting here. I do want to post-process with beam section results, so I'm going to turn that setting to yes. And then we're going to go ahead and ask for total deformation and equivalent stress, and let's evaluate those results and see how it looks. So taking a look at our deformation, definitely have a nice structure here. Let's scale up a little bit so we can see what shape it took on. We can see those inner struts really moving inward, and take a look at the stress themselves and see they are bearing the brunt of the stress here. I can manipulate this to get a good look at the beams themselves and see what kind of stress pattern they're under, and we can see quite nicely the individual beam elements showing different stress patterns. That's pretty much it. I think we got what we wanted out of this analysis. Thanks to SpaceClaim and Mechanical, it was pretty quick and easy.